Imagine a train is travelling towards you along a straight length of track. As this train sounds its horn, your microphone measures the horn's frequency to be 515 Hz. But you know that this particular horn, or this make of horn, is designed to emit a frequency of 500 Hz at rest. Now, by measuring the atmospheric pressure and temperature, you calculate the speed of sound in air to be 343 meters per second. With just these three pieces of information, you can calculate the speed of the train. So what we're doing here is taking advantage of a phenomenon known as the Doppler Effect. When a source of sound is moving relative to a stationary observer, the frequency of the sound will increase as the source of this sound is moving towards the stationary observer. But if this source of sound is moving away from this stationary observer, the frequency of the sound from the observer's point of view will decrease. So the frequency will decrease as the sound is moving away from the observer. And we'll see how this works visually with a simulation. And we'll do this in a minute. But in order to find the speed of the train, we can use this equation. So the frequency of the sound that you pick up as an observer is equal to the frequency of the source, which in our case is 500 Hz, multiplied by the speed of sound in air, divided by the speed of sound in air, plus or minus the speed of the source. So the speed of the source is the speed at which the train is travelling towards us, or if it's already gone past us, the speed the train is moving away from us. So this plus or minus part can be a bit confusing at first. But what it's telling us is that if the source of the sound is moving towards the stationary observer, so like it is in our problem here, the frequency heard by the observer will increase, and we should use the negative sign in the denominator. Now, the reason why we use the negative sign is that if the denominator has a lower value in this fraction on the right-hand side, the overall fraction will increase in value, and we expect the observed frequency to increase when a source of sound is moving towards a stationary observer. Now, if the source of sound is moving away from us, the observed frequency will reduce and will have a lower frequency than it is at rest. So this means that we must use the positive sign here in the denominator. So by using the positive sign, we increase the size of the denominator because we're adding to the velocity of sound here, and this will decrease the overall size of the fraction on the right-hand side. So pause the video and use this information to calculate the speed of this train. And we'll go through this step by step in a minute. So because the sound is moving towards us, we use the formula with the negative sign. Now we need to rearrange this formula to isolate the velocity of the source of sound. In other words, the speed of the train. So how can we do this? So if we multiply both sides of the equation by the denominator here, so the velocity of the sound plus the velocity of the source cancels out on the right-hand side, and we can put it on the left-hand side. Then we can divide both sides of the equation by the frequency from the observer's point of view. So now the frequency observed is in the denominator on the right-hand side. And now I've moved the velocity of the sound in air to the right-hand side and flipped the sign on both sides of the equation, so we can remove the negative sign from the velocity of the source. So now we can plug in our values. So the speed of sound in air is 343 meters per second. and we minus the source frequency, which is 500 Hertz, multiply that by the speed of sound in air, and divide that by the observed frequency, which is slightly higher than the frequency of the horn at rest. So we get a speed of 9.99029 meters per second, but if we round that up to 3 significant figures, we get 10.0 meters per second, which is about 22 miles per hour. So let's see what happens to sound waves as the source of the sound moves relative to a fixed observer. If we go to the O Physics website now, and I've got a link in the description if you want to have a look at this yourself. If we scroll down to the bottom, we find this app. So the observed velocity is 0 here, and we'll set the source velocity to something extreme, like 202 meters per second. And this will be moving towards the observer. If we run the simulation now, you can see that the wavelength in front of the source of sound has compressed down to around 0.41 meters from an original wavelength of 1 meter. So it's compressed by more than half. So in other words, if the source of sound was stationary and it was emitting sound, the wavelength of the sound would be 1 meter. But when the source of sound moves forward, the wavelength received by the stationary observer reduces by a value of the velocity of the source multiplied by the period of the sound wave. And the period of any sound wave and the period of any wave is the time for one complete oscillation. So the wavelength of sound experienced by the observer or seen by the observer is equal to the wavelength of the source minus the speed of the source multiplied by the period of the sound. So visually, what we're doing is this. The source of the sound moves forward a distance of the velocity of the source multiplied by the period. And if we have a look at the units quickly for this expression, we've got meters per second for the velocity, and for the period, the units are in seconds. The seconds cancel out, leaving us with a distance or a unit of length. So this shows us that our formula here is dimensionally correct. So if the source of sound is moving away from the observer, we add this expression, the velocity of the source multiplied by the period of the sound, and we add this to the original wavelength, and this gives us a longer wavelength and therefore a lower frequency as the sound is moving away from the observer. So if we go back to the O Physics website, you can see that the wavelength is longer behind the source of sound when it's travelling away. So we have the observed wavelength, but what about the observed frequency? Well, if we use this formula where the velocity of any wave is equal to the frequency multiplied by the wavelength, and we can rearrange this to isolate the frequency of this wave, which is equal to the velocity divided by the wavelength. We can expand out the denominator here with our wavelength equation above. So we got the frequency observed by the observer is equal to the speed of sound in air divided by this reduction in wavelength as the source of sound is moving towards the observer. We also know that the period of any wave is equal to 1 divided by the frequency. We also know if we rearrange our velocity equation here, the velocity of a wave is equal to the frequency multiplied by the wavelength. If we isolate this wavelength here, the wavelength of the source is equal to the speed of sound in air divided by the frequency of the source of sound. And we can plug this in to our formula for the observed frequency. So the observed frequency is equal to the speed of sound in air divided by the velocity of the sound divided by the frequency of the source minus the velocity of the source. In our previous example, this would be the velocity of the train divided by the frequency of the sound of the source. So in our case with the train, this would be the frequency of the horn, which would be 500 Hertz. So we can simplify this equation in 3 or 4 steps. So first, let's combine the denominator into a single fraction. We can do this because both terms at the bottom here are the same. So combining this, we get the velocity of sound divided by the velocity of sound minus the velocity of the source of sound divided by the frequency of the source. Now, when we have a fraction in the denominator of another fraction, like we have here, we can simplify this by multiplying the numerator, so the top of the fraction, by the reciprocal of the fraction in the denominator. So we can apply this to the top equation here, and we get the velocity of sound multiplied by the frequency of the source divided by the velocity of the sound in air minus the velocity of the source of the sound. And you've probably already noticed that this is the exact equation we used at the beginning of this video to estimate the speed of the train when the train is moving towards the observer. Now, if we do the exact same derivation again, but for a source of sound moving away from a stationary observer, we would end up with this equation. So it looks nearly identical, but the denominator now has a positive sign between the velocity of the sound in air and the velocity of the source of the sound, so the velocity of the train, for example. So let's test this out very quickly with the O-Physics app here. And what I'm going to do is I'm going to set the source velocity to a random speed. I'm going to leave the observer velocity at 0 here. The frequency of the source of sound is 343 Hertz. A train horn, for example. The speed of sound in air is 343 meters per second, which we've got down here. And I've set the velocity of the source at negative 99 meters per second. In other words, the negative sign here means that the source of sound is moving away from the observer. I've covered up the frequency heard by the stationary observer, and what I want you to do is pick the right equation and work out what the observed frequency is. And I'll uncover the observed frequency on the app in a minute. So because the source of sound is moving away from the observer, we use this equation, where the denominator uses the positive sign. And the best way that you can tell whether to use the negative or the positive sign here is what you expect the frequency to be if the sound is moving towards you or if the sound is moving away. So if the sound is moving away, we expect the frequency to decrease. And for the frequency to decrease, the observed frequency, we need this fraction on the right-hand side to be lower. And to reduce its size, we can increase the size of the denominator. And that's why we use the plus sign. So if we plug in our values now, so we got the frequency of the source, which is 343 Hertz. And I'll put units here of seconds to the -1. And I've done this so you can see whether the units balance on both sides of the equation. We've got the speed of sound in air, which is 343 meters per second. Then we divide this by the speed of sound in air, and we add the speed of the source of sound. Now, the reason why I haven't put a negative 99 here for the speed of the source of the sound is because by doing so, this would assume that the sound is moving towards us, but it's in fact moving away. So when we sum this up together, the observed frequency is in fact lower than the source frequency at rest, which is 266.17 Hertz. So when we uncover the frequency here, we see that it is 266.17 Hertz.